Hey guys, this is Undefinable Reasoning, and I have a treat for you today. A neodymium ring magnet, approximately 100 millimeters in diameter, with a 40 millimeter hole inside that will let you see quite keenly what is going on at the center of a ring magnet. Now, I know there are other videos of this on the net, but I don't believe any one of them use a ring magnet quite of this size. So it's quite difficult to see what's going on in the center with ring magnets because they have a rather small holes usually. So typically a ring magnet would be around maximum 60 millimeters in diameter, and the hole is usually much smaller than that. This one is 100 millimeters in diameter, so you will be able to see what's going on here. Now I am filming this in the room's lighting, so I'll change the color here to something a bit more visible for the camera. So there we go, and now we can see exactly what's going on at the center. You can see that we're having a centrifugal effect beyond the center of the magnet, and a centripetal effect coming into the center of the magnet. In fact, I'll prove this to you in a little while, but for now, let's take a look at the cross-section of this magnet when we reach the center. You'll see that the cross-section does change with your viewing angle, and that's because we're looking at it from such an extreme angle. Um, we're basically providing far more light to the left-hand side. The shorter distance of the light travels versus the longer distances, affecting the length. Now, what is interesting is if you were to take this magnet and start to spin it, and there you go, you can see that when you're spinning, you do have an interesting effect there. So now I want to show you something with regards to what is called the black spot, but isn't really. I'm not sure if you can see that, but that's not actually the center of the magnet. See, if you look at the reflection, you can see where the center of the magnet is, but the one that's on the screen right there is actually magnetism at work. So that's always a neat thing to see. I'm about to go show you a few more cool things, so just hang on there. So I'll show you something neat here. If I start to spin this magnet clockwise, it goes counterclockwise. If I go counterclockwise, it goes clockwise. You can see the field turning, right? Now, here's something very interesting. If you take this and you flip it over, and now you're technically reverse the polarity or whatever, right? But if you take a look at the spin that goes on here, if you're, it's going to take a little bit. There you go. I'm spinning clockwise, it's going counterclockwise, exactly the opposite as it was before. Counterclockwise, clockwise. So in fact, the spin, regardless of polarity, is always the same. So they're actually spinning in the same direction, despite the fact that it's the opposite polarity. So that's something neat, but I'll show you something even cooler next. Okay, so what I have here are two Royal Canadian Mint 99.99% finer than fine silver coins. Both are 1 ounce, and I'll be using these to show you something very cool. And of course, we still have the N52 neodymium magnet, our trusty old magnet here, and I'll be essentially disproving Lenz's law with them. But first I want to show you that these do in fact move the silver coins, even though they're not magnetic. You can see it's moving, right, without me touching. Now, if I take these two silver coins and put them on top of each other like so, you'll observe a very interesting effect. And this, in fact, disproves Lenz's law. If you go and put these coins right on top of each other and you try to move the magnet, only the top coin will move. Now the bottom coin won't move. Now you might be thinking, okay, well, this is magnetic shielding, right? Well, even if I take the magnet and I vigorously move it back and forth, it's not moving, right? Now, even if I were going to, give a geometric change, say if I were to arrange the magnet in such a way that the bottom one is there, you see, I'm moving the magnet well past where the first coin is, and the second coin is not even budging. So that's not Lenz's law at work here, and in fact I'll prove it to you using the ferrocell that it's not magnetic shielding at work here, and it's not Lenz's law either. It's actually something I'd like to call magnetic retardation because it's not in fact a matter of permeability, it's a matter of retardation. So what I intend to prove to you here is that the field is still present in the previous demonstration. In other words, it's not a magnetic shielding effect that's affecting the second coin not being moved. Now I want you to pay close attention to what happens when I put the silver coin on top of this magnet. You'll see that the petals actually get larger and the field gets spread over a much wider area. It's still the same field, it's still penetrating. It's just spread over a much larger area, and the reason for this is electromagnetic retardation. The field is essentially being retarded, or it's compressed flat against its plane of inertia. It's still penetrating, it's just having a hard time doing it, essentially. It's kind of like how light changes its incident angle depending on the substrate. It might be a slightly different angle. It's the same concept with magnetic fields, and this is also another similarity that magnetism and light share. So yeah, the field is still there, it's still penetrating. You can even see the so-called dead zone, which is really just centripetal magnetism there. So the field was there, but the second coin wouldn't move. Why? Because it's not Lenz's law. It's the dimensionality or the geometry of the field is what's actually changing here. And once it's passed through the silver, it was already in a state that was acceptable for the next layer of silver. And you can also see that the actual field goes further than it did before. You can see evidence of the geometric changes here.